production techniques. And these farmers are using effective climate-smart practices thanks to nuclear science and technology. These people are just a few of the millions around the world who have benefited from the IAEA's Technical Cooperation Program. This program helps countries get the best out of nuclear science and technology while strengthening radiation safety for the protection of people and the environment. It provides the knowledge, equipment, and networks that countries need to make progress towards the UN's Sustainable Development Goals. By building national capacity, the Technical Cooperation Program helps ensure countries are empowered to address their most pressing development challenges. Increasing access to cancer care. Fighting infectious diseases. Improving nutrition. Growing stronger crops. Increasing farming efficiency. Managing insect pests. Examining animal health. Providing clean power. Planning energy security. Supporting nuclear newcomers. Advancing small modular reactors. Tracking limited supplies of water. Providing data to protect oceans. Alongside all this work to bring the benefits of nuclear science to the world are strong cross-cutting commitments to address climate change, improve radiation safety, and empower more women to work in this fascinating field. The Technical Cooperation Program also has the flexibility to respond to critical situations quickly, from global pandemics to earthquakes and other disasters. At any given moment, there are over 1,600 technical cooperation projects in around 150 countries in the areas of health, food, energy, water, and much more.
Thanks to the IAEA's Technical Cooperation Program, our member states can enjoy the many benefits of the peaceful uses of nuclear science and technology. This program makes a concrete difference to the lives of hundreds of thousands of people every year.
The IAEA responds to the world's evolving needs.
Hello, Helena.
Hi.
Hi, nice to see you.
Nice to see you. Good morning. Good morning, everyone.
Good morning.
Welcome from Vienna.
And hi from Beijing. And you can also see Professor Zhang and Professor Wang.
Yes, this is
Good
great.
morning.
Good morning. So, dear colleagues, dear speakers
Yes.
and participants, on
Yes.
behalf of the International Atomic Energy Agency, it is my pleasure to welcome you to the 16th ANENT webinar on nuclear technology application, innovations and opportunities. This event is a great example of how we can come together to share knowledge, promote innovation, and learn from each other. I would like to thank Anand and our colleagues from Harbin Engineering University for organizing and supporting this webinar. Today's topic, from nuclear materials and medicine to wider applications in agriculture, industry, and public safety, show the many ways nuclear science is helping to solve real-world challenges. These technologies not only support energy security and healthcare, but also contribute to food security, environmental protection, and sustainable development. At the IAEA, we are proud to work with our partners in Asia and around the world to strengthen education, research, and international cooperation in the peaceful use of nuclear technology. I wish you all a fruitful and engaging webinar. Thank you.
Thank you very much, Helena. I should introduce Helena a little bit first. She's from the Department of Nuclear Knowledge Management from IAEA. So actually, she's speaking on behalf of IAEA. Thank you.
Thank you.
And ladies and gentlemen, welcome to this free webinar about nuclear technology application, innovations, and opportunities held by ANANT, the Asian Network for Education in Nuclear Technology, which is fostered and greatly supported by IAEA. And thank you, Helena and Marina, for making all this happen. First, please allow me to introduce ANANT a little bit. Here, I cannot play the PPT, but I will say something about ANANT so that you have a general impression. ANANT was established in 2004 and has been running for over 20 years. And now ANANT operates an e-learning platform with various nuclear science and technology learning materials. And you're welcome to visit the ANANT website through the web portal or other social medias. You will find abundant learning materials and get information about our upcoming free webinars in nuclear technology field. Okay, today we are honored to have two speakers from China. And the first speaker is Dr. Tian Zhang. Dr. Zhang gained his master's degree from the University of Manchester in 2012 and a doctor's degree from RWTH Eton University. He then started working in Harbin Engineering University as an associate professor. His main research interests lay in nuclear reactor fuel performance and safety, and target design for accelerators and neutron sources. Okay, Professor Zhang, the floor is yours. Can you try if you can play the PowerPoint?
Thank you, Ms. Go, and I will try to share my screen, and hopefully you can see it, and everybody can see it and hear me clearly and loudly.
Yes, no problem.
Okay. So, thanks a lot for the introduction, and it is my great honor to deliver this webinar on the topic of nuclear technology and applications, innovations, and opportunities. So in today's webinar, we plan to cover several topics, and we would like to start from the very beginning, like the fundamentals of nuclear science, to those who are new to nuclear and who do not know much about nuclear. And based on that, we would like to, on my side, I would like to give some introduction on the nuclear materials for energy and innovation, and followed by nuclear medicine's revolution and healthcare. So let's start from the fundamentals of nuclear science. Well, the fundamentals of nuclear science really discovered dated back to about 130 years ago, and it's from the famous scientist William Conrad Roentgen. So his discovery accidentally of the X-ray really started our understanding of radioactivity. So it was from an accident. So he was really starting some kind of behavior of Lorentz in experiment, and he used this Crookes tube with upcut paper in a very dim room. And what he want to say is that with this paper covered, there's nothing happens. So that is what he want to say. However, something really unexpected happened. The sparring target suddenly flashes something, and he don't know what is it. And this flash are how it comes and what it's for is interests him. So from his study, he found out a mysterious lights that are not observable, and he named with the word X, so X-rays. And here is really the Crookes tube he used in the experiment, and this is actually the first X-ray figure of uh, his wife made by this kind of technology. So things then developed very quickly after several scientists and like Becquerel, Pierre and Marie Curie, and the greatest scientist Ernst Rutherford. They discovered the radioactivity and extracted some radioactive isotopes, and in the end, followed by Rutherford classified of different kind of radiations as we are using it today, like alpha, beta, gamma, as well as X-rays and neutrons. So that is something we are standing from. And radiation. So this is something that we are quite, let's say, scared of to some people, particularly who do not know, but it's actually everywhere. It's from the sunshine, from the airs, from the food. And one example I would like to use very often is to use this case of banana. So we eat banana a lot, and we eat it almost every day and every week, but it contains sort of radiation from potassium 40, and it contains every 5 grams it has a radioactivity of 65 becquerel. So we say radiation is not something that's far from us, but it's all around us everywhere. Okay, so this radiation discovery followed by a long series of new scientists and new discoveries in the early 20th century, including Rutherford, Einstein, and Chadwick and Strassmann. A lot of people discovered many things, including the E equals mc squared, very famous equation, and neutrons and splits of the uh, nucleus into several isotopes and some neutrons. And I 1942, another great scientist, Enrico Fermi, achieved the first nuclear chain reaction in the playground of University of Chicago, the Chicago Pile 1. So radiation is, what is it? Fundamentally, it's the process that unstable atom turned into stable atom. And in this process, something occurred or emitted from this process, which are alpha rays, beta rays, or gamma rays. And then in this process, what we find is that for the nucleus that made of protons and neutrons when they combine together, there are some mysterious defection of mass. So by this mass defection, there is energy converted. So that is how things are connected. Discovery of isotopes, discovery of protons, neutrons, and discovery of all the radiations. And then they combine together to the famous equation E equals to mc squared. So this mass defect discovered a, a reality that mass could be converted to energy. And due to the very large speed of light, very small mass can convert to a lot of energy, and in this process, this energy can be then converted to other applications. So in, from this, we can see there are two different ways of mass defect. We can, let's say, merge two light nucleus together, like from helium and deuterium to lithium. So this is what we call fusion today. Or we can split a heavy atom like uranium-235 to a less weighted nucleus like captain of iron. So that's what we call fission. In this process, a lot of mass are converted to energy, and this energy is what we are using. So Fermi smartly using this physics and built a great machine, which we see here, Chicago Pile 1. What Fermi used to describe this pile is a crude pile of black bricks and wooden timbers. So you see here, it's a pile. So it's why it's called Chicago pile, because it's really a pile and a lot of black bricks and woods surround it. So if we take a closer look into this Chicago Pile 1, what we are going to say, it's made of 330 ultra pure graphite brick. So that is what we are seeing, black bricks. And 4.9 tons uranium metal and 41 tons uranium oxide, which are included in this inside it. It has nearly zero power, no shielding, no coolant, because people know nothing about how it really works. So they carefully designed it with a very low power. And in the side of it, there's a cadmium control rod that be used to control the reactor to slowly make it achieve reactivity, criticality. And X-Man here, standing here, prepared for a scrap, so in emergency cases. So on the day, December 2nd, 1942, Fermi was standing here to see the recorders, and George Well is standing here slowly pulling out this cadmium rod till the moment Fermi sees some recordings or signals here to say neutrons are continuously emitted from this large pile of things. And this marks the discovery of or the creation of nuclear reactors, and is still today we are using the similar mechanism to build nuclear power reactors. So fundamentally, a nuclear reactor is a device used to initialize and control a self-sustainable nuclear chain reaction, and different from then, different from the Chicago Pile 1, what's are here is it really brings energy out. So we have to use some heat carrier to put it to heat exchangers and into other applications such as electricity or other things. So till today, there are a long development of nuclear reactors for 80 years, and it's after the Atomic for Peace action, lots of different reactors are designed and put into commercial use. Like today, we are having a lot of light water reactor around the world, and also other reactors under development, such as high temperature reactors, fast reactors, molten salt reactors, etc. And up to the latest data, so which you can look it up from the IAEA PRIS database, we are saying the nuclear reactor under operation is nearly 420 with an installed capacity of 375, nearly 375 gigawatts. And still we have a lot of reactors under construction with a lot of capacity to be installed into the energy mix. So today we have approximately 10% of world's electricity are supplied by nuclear power reactors, and most of them are at a very large scale of gigawatts and produce online baseload electricity supply. So that is what we are sort of familiar with. So the story of power reactors, when we are talking about nuclears, we are thinking of that very often. However, there are a lot of other usages of nuclear technology besides electricity. It can be used into various disciplines in our daily life, like medicines, environment, food and agriculture, even arts and archaeology. So it's everywhere. So let's get back to the historical line of development of nuclear science. At here, this point, after Roosevelt recognized theorized a neutron before Chadwick really identified neutrons in the 1920s, the Lawrence discovered or invented cyclotron from the University of Berkeley in the US. And he uses machine to report the production of nitrogen-13 with a half-life of 10 minutes. And thereafter, the cyclotron was used up to produce several other biology important radionuclides like carbon, phosphate, and sodium. So besides this timeline we see here for power reactors, we also see this timeline for nuclear isotopes in parallel. So today, nuclear medicines are also widely used in our treating and diagnosis of people's health and cancer and many kinds of diseases to figure out what's wrong with your body. So this is another line. So this cyclotron here is what's being invented by the Lawrence, very simple and with continuous injection and extraction, and it can can have multiple usage according to acceleration voltage. And here is what we have today. So this seems to be two parallel lines that are not crossing with each other. So one is power reactors, a very large machine with piles of uranium and a very complicated control system and supplying electricity to all over the world. And this is a small machine can be put in a small room in the today's hospital using for diagnosis and using for therapies, etc. So looks like they are not converting with each other. However, in the reality, they are really closely coupled with each other. The usage of nuclear accelerators like cyclotrons and other accelerators can be a great support of development of nuclear power plants. And the nuclear power plant, on the other hand, can be used for the supplying of radio applications into health and other things. So they are looks like parallel, but not really. So today we have selected two examples from my presentation showing how these two lines are crossing with each other. One is the nuclear materials for energy and innovation. So talking about nuclear materials, we can easily think of nuclear power reactors. So in the nuclear power reactors or the materials in the nuclear industry, we are seeing a lot of different things. Let's take a look of this figure. So it shows the different materials being used in the nuclear power plants for typical PWR. We see different kinds of alloys, different kinds of stainless steel, and different kinds of fuels, pellets, and cloudings. So for fuel material, we have a lot of candidates, and for the cladding materials, we also have quite a number of candidates too. So these are a lot of materials. And these materials are undergoing a very harsh environment. So typically in the reactor, it has very high temperature. So for PWRs, it can reach approximately 1000 degrees C, and in some high temperature reactors, it reaches 130, 40 under accident scenario. And it has a very high and complicated radiation fields, including neutrons, gamma rays, alpha beta rays. A lot of things are combined together with very strong intensity. And in a nuclear power plant, we see this typical pressure vessel for PWR. It has a height of over 10 meters and a width of over 4 meters. This is a big thing, and the materials uh, have to bear a lot of stresses from the weight. Okay, it's all stainless steel and it's all metal, very heavy, and it will be undergoing fluid movement with complicated compositions. The coolant and the chemical add-ons, and sometimes the debris, and also very high temperature uh, gradient. So in the center of the core, it can be over 100 degrees C, and here to the turbine machine is a turbine machine building. It reaches about 40 degrees C that people can enter. So the temperature gradient is very, very high from very small radius. And also the incident energy of radiations, typically neutron, can cover a really extremely broad range about 13 orders of magnitude from thermal neutrons to fast neutrons. So materials are undergoing at various extreme conditions. So under these conditions, materials have to undergo mechanical failure, probably, like fatigues, fractions, and it may have corrosions, temperature variations, and corrosions and the variations make things even worse. And one particular things related to nuclear applications, materials have to deal with the radiation damage. So the radiation damage is let's say dynamic stuff to change the material properties. It may lead to the swelling of materials, as here we see, here is unirradiated and here is irradiated. And it may have some crackings. So here, the few pellets may crack into several fragments, and in under accident scenarios, and may undergo corrosions or crackings, or it may have reconstructions, like here in fast reactors, a central void is created due to the radiation, or hydrogen pickups causing embrittlement. So various extra effects could be added to normal materials performance. And these are all dynamically induced with radiation. So incoming radiation, like we can take it as some kind of particle, and this particle may bombard a material at a certain energy and losses energy via collides like and interactions. This could be seen as sort of Bolyard models that causing one thing enters and it interacts with the materials causing displacement, and this displacement will further propagate and generates pairs, moving particles, and vacancies. So all in all, these vacancies and interstitials causing changes of material properties in the end, and all of these are, let's say, connected to one parameters we use as a key indicators, which is called displacement per atom. So which is the atom displacement according to the flux and cross sections at different energy levels. Okay, so what do we have now? We have a lot of materials, we have extreme conditions, we have some key indicators, and we want to build a nuclear power reactor. So lots of materials are in need, particularly resistant to extreme conditions like temperature, pressure, and gradient. And as nuclear power reactor aids something producing heat, we want something that has good conductivity and neutron cross section. And under extreme conditions, we would like to have the material resistant corrosions, embrittlement, and in the end, to protect the publics, we want the materials to be able to retain efficient products. Also, for any stakeholders, we would like to have some materials that are costly, affordable, and fabric. Particularly in the future, we want to have new materials with even more extreme radiation environment. As we see here, today's PWR, we are having a temperature relatively low and a dPA relatively low. However, in the future, what we want to have is an extremely high dPA and high temperature. So how can we select materials? Normally, there are 4 stages from selection of potential candidates. In the lab scale, we do some experiments and we have to be iterated and feedback and scaled up to do environment. And in the end, qualification and demonstrations, tests in reactors and real in radiation conditions. So this is what we do traditionally. And this process takes about 20 to 25 years. So that is what we have done in the 1950s and 60s with a very highly empirical nature. So irradiations have to achieve similar DPAs. So we have to put the materials into the reactor and bombard it, waiting for 5 years and check out what is it looks like and is it good, is it bad, evaluate it and trial and error. All this iteration process very slow and very harsh. However, we have a great need in short time. So this great need is that we want to have, as you still remember, here, we want to have a reactor in generation 4 in probably 15 years. And also the demands of climate change requires a new materials or new facilities being built in more safe and economic manners in 10 years or 20 years. So we do not have the time. We want to accelerate this. So here we have something that can be useful from the nuclear technology. So it's longer radiation time in traditional testing reactor, and we have more candidates materials due to development of material science, and the regulators today are more knowledge and more strict to understand based on the knowledge we have accumulated in the past and the experiences. So traditionally we have testing at like testing reactors with 10 DPAs or 20 DPAs a year, which could achieve like here 150 DPAs in 15 years to understand how materials really behaves under radiation. However, by introducing iron accelerators here, we could achieve much more highly DPAs per day. You look at here. So we have 20 DPAs per year in a testing reactor, and by iron accelerators, we can achieve something like approximately 100 DPA we want. So this is a great news for material scientists that to develop new materials. Here we have a figure. So left is what's being irradiated in the reactor, and the right is the irradiation from an accelerator. We see that they are quite equivalent at the same DPAs. So by using an accelerator, we could innovate a way that's being useful for new materials. So By ion beam irradiation, we can achieve relatively high DPA rate, 3 orders than the neutron, and a very low activation and cost because we do it in the lab, and we do not need to build a reactor. We do not have to control the reactor performance, blah, blah, blah. So just do something in this room. And it is very effective to study several separate effects. For instance, we just want to study swelling, or we just want to study about corrosions. We can use that. The only disadvantage or drawbacks is it's an ion accelerator. It can be only working on very small samples due to the very low penetration of ions. So that's its drawback. So all in all, it does not really able to replace the acceleration, replace the radiation in the reactor in the end, but in this process, the selection and lamp scale and the improvement scale, it can much more accelerate the process. So here we have the images from the ion accelerator at different DPAs. We do the acceleration, we do phase, and then we examine by the TEMs and do data analysis. Okay, what's more? So what do we achieve here? So this ion accelerator is not only thing we need to do, but also it have to be coupled with the modeling. So by ion accelerators, we could do a lot of experimental data for characteristics and also to have multi-scale modeling, then to investigate the model for the fuel performance code or material performance code at the first principle scale to engineering scales. By this way, we combine the ion accelerators with acceleration and to have good predictions of fuels behavior or materials behavior at different scales and accelerate this process much more. And the next topic I want to share is about nuclear medicine. So it's a topic that reactors can help healthcare. So fundamentally, the radiation interact with cells that by direct or indirect interactions and causing by bombarding the DNAs or generates RNAs that may have chemical reactions with DNA chains. But our DNAs has also a probability to recover itself from the cell cycles. So it takes probably 6 hours post-radiation to recover at different stages, and it's a cell cycle dependence. So different cells may have different resistance to the radiations. Taking the advantage of this, we could do a lot of things in diagnosis and therapy of nuclear medicine. So nuclear medicine is a medical ways that using radioactive traces to assess the body function and to diagnose and treat disease. So for diagnosis, we have today gamma cameras, single photo emission computed tomographies, SPECT and PET. So here listed some figures that being used from SPECT. We are seeing here for this mouse, there are several key points that are examined showing the bone tracers to see its structure. And also here we have the whole body PET scanning using fluorescence 18 FDGs to show here the patient may have some issues with his liver as cancer. So this is what nuclear technology can help us for this. And for diagnosis, is very often related to the nuclear radionuclide imaging to obtain a picture of distribution of radioactively labeled substance within the body after it has been administered, like injection. So today, the most widely used isotopes here is fluorescence 18 that being used to check many things, and it has after it has been injected into human bodies, it decays and generates radiations could be detected by our detectors here. And then this detection signals are converted into by the computer into figures, and we reconstruct the image to show to the doctors what happened inside the patient's body. So besides this way, there are also radiation therapies used for treatment of cancer. Typically, there are, let's say, bone nutrient capture therapy and proton therapies. And this kind of treatments taking the advantage that protons may have a black peak to concentrate most of its energy into the ends of its penetration. So it's like here, when we have a proton injected, most of its energy just deposit at the end of its range. So if we are able to strictly control its end into the tumor cancer cells, we could let the energy deposit or the radiations deposit inside the tumor cancer cells and kill the cells without harming the healthy tissues like here. And also in another way, we could also try to take the advantage of foreign and neutron interactions with large cross sections, somehow trying to deliver a kind of medicines that can only interact with tumor cells. So the boron medicine is manufactured and injected, and it interacts with tumor cells, causing and when the nutrients bombarding, this reaction may happen just kill the tumor cells instead of health cells. So in this way, we could also treat the cancer. In both of this way, what we are requiring is different radioactive nucleus with different half-life, and to producing this kind of nucleus, what we are need is different facilities. So here, the nuclear reactor can be used for isotope production because many reactors has the capability to generate very high neutron fluorescence. And this neutron fluorescence can be used to bombard different targets and generate neutron-rich isotopes, typically like technetium-99m, which are bombarded from molybdenum. And besides reactors, we can also using the particle accelerators to bombard protons, deuterons, and R particles or heavy ions to generate radioactive materials for medicine use. Okay, I think that is what I want to deliver about these two parallel lines. And of course, there are later introductions about what I talked, some references. And thank you for your attention. And if you have questions, we can discuss later. Thanks a lot.
Thank you, Professor Zhang. Professor Zhang talked about the fundamentals of nuclear science, nuclear materials for energy and innovation, nuclear medicine, which is revolutionizing healthcare. Thank you very much. Very clear, general, and comprehensive introduction. Thank you very much. I would like to remind our audiences that there will be question and answer time after both of the presentations are done. So, and you can also input your question in the chat box area, which will be convenient and clear for professors to prepare their answers. Thank you. Next, I would like to welcome our next speaker, Dr. Xiang Wang. Dr. Wang gained his master's degree and PhD degree in Technical University of Munich and started working in Harbin Engineering University from 2017 as an associate professor. He focuses on the multi-scale and domain coupling of advanced energy system, as well as particle beam physics and application. The floor is yours, Professor Wang. Oh, we cannot hear you yet. I can see that there are several pieces of information in the chat area. Please do not click them. I'm not sure if they're safe. So be careful before you click all the links. OK，还是听不见。麦克打开了吗？是不是这个软件上有一个，就右上角有一个麦克风 ？There's a microphone logo. I think we have some technical issues. Let's try again. 还是听不见。王老师能听见我说话吗？哦，但是我们听不见您说话，是不是那个电脑有一个音频选项？我看看啊，有一个更多，就是上面那一排更多里有一个音频设置，会不会是那儿需要设置一下呢？Now we have some time. I would like to introduce Anant a little bit. Oh, wait a minute. 王老师，我先介绍一下 Anant，要不？
喂，
可以了。喂，
可以了，
现在能听见了。我现在能听见你说话了。Okay, I will stop my sharing. Oh, please let me say something about Anand. Okay, this is Anand. And you can scan this code to pay attention for our upcoming webinars. And here are some introduction. We have 21 members and 7 collaborating member organizations too. And here is how to become a member. Here are some information. You can take this down and contact us. Okay, I will stop my sharing.
Okay, so can you see my screen and also see my voice?
Yes.
Excellent.
No
excellent.
problem.
So let's start. Good morning, good afternoon, and good evening, everyone. Sorry for the small technical issue. Now I think we are all ready to talk about the following parts of the nuclear technology applications, innovations, and opportunities. So especially, I would like to address in these four aspects: energy security and climate mitigation, agriculture and food security, industrial and environmental applications, and public safety and global challenges. So maybe you can see that I'm actually in a hotel room because I'm in a business trip. These days, I have been in different cities in China to visit different enterprises who are working with nuclear technologies. And as I have seen and as I have known, only, well, the applications in one enterprises cannot be fully explained or fully elaborated in this half an hour. So I would like to say that here what we can see or here what I will introduce is very fundamental and only a very small aspect from what we can do with nuclear technology. Okay, this is, I think it is some inspiration of thoughts. And after this kind of lectures, you should or you may to explore more from internet and from some mediums. So I will start from the energy security and climate mitigation. So here, what we need to know is that the energy is the more the better, because it is how we make things, it is how we move things, and it is how we warm our home and prepare foods. Okay, it is how we make the world better. So when we see these pictures, we can see that I will try to use a pen here. Yes, here. This is the sustainable goal from IEA. As we can see, in the center is the energy. Okay, the energy supplies everything around. And here we can see that this is a picture of the desert in China, but here you almost hardly see the desert because we have these wood panels here, solar panels here, and the solar panels will shadow the sunlight to lower the temperature under here, and also the water to clean the solar panels will make the grass grow here. And when we have grass, when we have animals, so the desert will be light again. And here we can see the electricity generation. So everyone knows that China after 2000 has a massive growth. Why? Because the energy supply increases. Here we can see from 2000 to 2023, China has increased from here to here, the electricity generation. So that is why we have power to produce, we have power to build highways, trains and everything, okay? But still, it is not enough because what we can see from here is that the per capita electricity generation by source. Here we can see China is still here. It is far more or less than other countries, right? So this is what we need to catch up. And the world is facing a dual challenge. One hand is the meeting the growing energy demand, and one hand is drastically reducing the greenhouse gas emissions. This is the goal to sustainable develop our world. And this is also what we have signed in different climate conferences. But a lot of countries may have the question, if we, for example, limit the production of the gas emission, will this sabotage our economic development? But I think that this should be checked individually. It means that we can use the energy sources that produces less or will not produce greenhouse gases. And at the same time, we supply our industry, we supply our life with strong energy power. So this is how China is doing. So every country can take this as an example to solve this kind of energy dilemma. currently, the fossil fuels, as we can see, it still dominates the energy mix, but they are unsustainable, pollution intensive, and hard to decarbonize. And currently, as we can see, the world is not peaceful, and we have different situations here. For example, China needs to import oil and also gases from all over the world, and this can be very dangerous on the ocean. So we have to reduce the import of the oil, these fossil fuels, but to produce some energy from China mainland by ourselves. As some of you may know that China has permitted another 10 reactors per year, okay, this year. So as you can see, every 10 reactors per year, very fast we will have a quite high capacity of the nuclear power production. So the energy security and climate mitigation have become intervened priorities, okay? And we therefore have to ensure that every energy sources can be used by us to reach our goals. And then the nuclear energy is one of the best optimal optimist solution for us, because the nuclear energy uniquely addresses both, it delivers the stable power, and also it produces near zero carbon emissions, okay? This is very optimistic. So for the nuclear power generation, just now Professor Zhang has introduced some basic ideas. Currently, we mainly use the fission power, the nuclear fission, to generate power, okay? But now there are a lot of companies, institutes in China are focusing on the fusion power, and approximately, in the next 20, 30 years, it can become true. So the principle is that the nuclear power generation harnesses heat from controlled nuclear fission reactions and to produce steam, which drives the turbines to generate electricity. Okay, so this is actually the same or similar with all other kinds of power plants that we boil water. So what kind of advantages of nuclear power? Here are some features. For example, we have the high energy density, we have the low carbon emissions, and we have this high stability. So this is a very schematic diagram of the nuclear power generation of the PWR, pressurized water reactor. Of course, we have also other kinds of nuclear reactors like BWR, HTR, or molten salt reactors, lead reactors, and so on and so on. So only in the generation 4 nuclear reactors, we have 6 types, and don't even mention that we can mix them together. We can have different combinations to choose the fuel, to choose the coolant, everything. So we can make our own optimal types of nuclear reactors for different applications. Here are some very clear examples. For example, this one is the space reactor that we use in the space to propose. Okay, and then this one is a ship reactor, marine reactor, that we can put the nuclear reactor in the ship to supply power to some islands, to the industry, near shore, and so on and so on. These two are two designs for the truck reactors or vehicle reactors. It means that we can put this kind of reactors in the truck to supply power and to make function as some kind of emergency power. For example, somewhere has the power shortage or have some earthquakes, then this truck can carry this energy source very fast to the site and to provide power to save people. Okay, this is very important and also very promising. And here we can see that this is a kind of technology roadmap that from 2020 to 2050 means that though we have currently mature nuclear energy, nuclear productions, but still we are evolving, okay? The technology is evolving and everything related to that is evolving. So it means that we will have much safer and also more robust nuclear energy generations in the next decades. And here are some roadmaps some technologies that we need to conquer. Okay, so here we can see in the future, we assume that at 2050, we will solve the problem of fusion and to generate unlimited energies. So that will be the beginning of a new era. And the nuclear power can be used to ensure the energy security. So what is actually the energy security? It is an evolving concept now widely understood to encompass 5 key dimensions. First, acceptability. Second, accessibility and affordability, availability, and sustainability. It means that first, you have to accept this kind of energy source as for your energy fleet or for your energy mix. And then after that, you can have the access to use that. Okay, for example, for some countries, they have very good source for the solar power. So the solar power may be the main energy source for their country. And for some country, they have cores, and the core may be very important for them to build these fire plants. Okay, so the nuclear power had to shape themselves to fit into these different dimensions. And affordability, as we know that the nuclear power is currently very expensive at the beginning, though they will have less maintaining cost and have a higher income up in the next 30, 40 years. But at the beginning, the investment is very, very high. So this can be a barrier for new coming countries to get into this field. So this affordability is also a challenge for the nuclear power. And the availability means that we have to use that safely, right? And sustainability means that we have to have the enough nuclear fuel for that. For example, currently in China, in the Hubei province, we have the thorium reactor demonstration project. It means that we will change our main nuclear fuel from uranium to thorium. It means that, well, because China has planted much more thorium than uranium, and therefore we can use thorium as the fuel to sustainably develop our nuclear fleet. So this is important. And also we have to treat, for example, the spent fuel and to use fast reactors to reuse this to reuse these resources and to use them all. In this way, we can have, for example, sometimes we can also have breedings, means that we burn the spent fuel and we breed new fissionable nuclides to be put in the nuclear reactors. So these 5 key dimensions will have a very strong requirements on the different source of energies, and the nuclear power, which is very suitable to be developed and also to consider to secure for your energy security. So this is some examples. For example, how nuclear power enhances energy security. First one is stability. Okay, the nuclear power is very stable. As we can see here, if for example, normally during one day, we will have a higher power requirement at noon because, for example, now I'm in Shenzhen city and it is very hot. So every office, every building is having this air conditioner. And at night, well, the factory will stop, the people will sleep, so the electricity consuming will be less. And if, for example, we use this renewable system, well, the sun comes out at daytime and goes down at night. So sometimes we have these fluctuations, and also for the wind, it is not always a bit sufficient to generate electricity, so it is also fluctuated. But this is our demand, what happened, okay? So we have to use this nuclear power as the base load. This will be very, very strong supply. And also, we can have that the capacity factor per energy source in 2020 means that though you have built a factory, you have built a power plant, but what is the percentage of usage, okay, you have used to generate electricity? Here we can see the nuclear power, okay? The nuclear power can generate electricity every day, every minute, every second. It is not like for example, here we have geothermal, wind, solar, and so on, okay? So as we can see, here is the wind and solar. And then we can see that here are the different coasts, and also here is the different, for example, the different power stations. Means that in the next decades, we are trying to replace the current existing fossil fuel power plants to the nuclear power plants, so that we can have more secured energy support. And also the low carbon characteristics and emission reduction contributions of the nuclear power is obvious. That we can see, for example, we can see from different figures, we can see different statistics that the nuclear power generates electricity only with very low life cycle carbon dioxide emissions, and also very few, for example, sulfur dioxides and so on and so on, and also the nitrogen dioxides and so on, okay? And one case is that, for example, here in China, Shidao high temperature gas cooled reactor, it is a demonstration project. It has been put into operation in 2021, and it provides over 500 Celsius degree steam to surrounding chemical or industry plants. And also in the winter, this kind of heat can be used for the heating, okay, for the room heating, for the residence heating. And this reactor has reduced carbon dioxide emission by approximately 200,000 tons annually. This is quite a large amount. And of course, we can combine nuclear with renewable energies. It means that the nuclear energy is not exclusive. Okay, it can be combined with different energy sources, and therefore to make the good maxima. Means that, for example, here we can use this kind of grids to balance in some scenarios. And also we can have this low carbon hydrogen production by the fuel cells and so on. And also we can have this energy sector coupling. It means that we can couple different energy sources, so that we can, for the remote or off-grid regions, which can be very useful and also very practical. So the energy is actually the main application of the nuclear, but also in other fields. For example, here we can say that the agriculture and the food security. Okay. So the base principle of the nuclear application in the agriculture and food security is the radiation. The radiation will change the DNA, will change the inner chemical materials and biomechanical materials in the cell, and therefore make changes. So here we will have some traditional radiation brilliance. It means that by using gamma and X-ray to boost mutations, and also we will have a heavy ion and proton beam to breed. It means that we can have different, just now Professor Zhang has showed you that, for example, for the heavy ions, we will have this bright peak, and therefore we can make the minimal damage to the surrounding tissues, but we can target at some certain points. And also we'll have the space radiation because, for example, currently China has its space station in orbit of the Earth, and we have launched rockets to bring our seeds and also some tissues to the space station to let the space radiation to boost the mutations of the seeds. And after that, when we, for example, bring these seeds back to the Earth, we can select which ones are better, which ones are bad, and then we can have some new new types of agricultures. Here are some cases, for example, for these onions, after the radiation, some kinds of onions will have different characteristics. But sometimes it will be smaller, sometimes it will be bigger, okay? But it changes very, very fast. It means that, well, though it is smaller, but it tastes better, okay? It tastes sweeter, and there's no pungency. In this way, well, for example, for the Indian people, they love to eat onions, and for some other countries, right? So this can be cultivated and to produce some new types of onions and also different kinds of products. Here is a case for that we use carbon ion beams to irradiate methionized soybeans. We can see that after the radiation, okay, they can enhance the efficiency and improve drought tolerance and stress adaptability. Means that we can have some better plants. For the irradiation sterilization, it has also been quite widely used in the food industry. For example, the gamma rays can generate free radicals and bioionizing water and biomolecules, so that these things will damage DNA and to kill these to kill these bacteria or some sectors and so on, so that we can keep our food fresh and to keep our healthy. Another kind of beam is that we use electron beam sterilization. It means that we use the electron beams to radiate. For example, here is the accelerator, and here the beams will go down through the floor and to scan the product here, so that the product will be transferred from here to here and go through these electron beams, and then they can be radiated. These products, I think some of you have seen it. This is the instant noodle. Next time when you buy the instant noodle, please check, okay? On the surface, on the top of this product, you may find the words that, okay, some powder package has been irradiated, okay, to kill the bacteria. And this one are some just instant foods that we can eat everywhere, we can eat anytime. But the important thing is that we have to keep them from bacteria, from some harmful bad stuff. And this is the Chinese medicine. This is also the Chinese medicine. But so because this Chinese medicine are pure natural products, so we cannot boil them, we cannot use high temperature, but we can use radiation. Okay, we can use radiation to kill bacteria, to kill bad stuff, and to leave the useful material inside of this medicine. So this is also the soil disinfection, because every year we will have this bad bacteria or something in the soil, and also some bugs will have their eggs also in the soil. So after this irradiation, the soil can be disinfected and can be used to grow crops. This is also the sterilization of seed potatoes. It means that after this, the potatoes will not grow, and therefore we can keep them for a longer time. Okay, and then we'll have this isotopic tracer technology. Here, actually, not only two categories, but actually several categories. Okay, here we can see from these pictures. This one is very clearly to demonstrate how the carbon-13 and carbon-14 are used or can be used to trace. For example, for all the living things, the carbon-13 and carbon-14 are cycling inside their bodies. But if they are dead, okay, if they are dead, the carbon-13 will not anymore cycled, so it will have to decay. And we can check how much carbon-13 are left so that we can check, okay, when that this thing has passed away. So we can use this kind of technology to find out, for example, what the age of some antique comes from, and also we can to check when has some very famous people died. This is a very famous painting, which is the death of Napoleon. Of course, Napoleon is not dead so early, so we cannot use carbon-13 to test, but we can know how Napoleon died. How? Because in history, we have heard that the Napoleon was died due to some chemical materials. But actually, when the researcher from Italy has taken his hair and put it into some neutron activation methods, it turns out that the chemical materials, the poison chemical material in his hair is not as much to kill him. Okay, so this may be a rumor. And also here, it is a painting on the stone in the stone cave. We can use this method to find out when was this painting here. And this is how we do that. For example, for some very, very long period, for example, we have to find out what is the age of the Earth. Okay. In this case, the carbon-13 is not enough. We have to use what? We have to use uranium. This is the uranium lead. Okay. To use uranium and lead to find out what is the age of the Earth. So at last, we will talk about the industry and environmental applications. As I have said, there are a lot of applications, and here are only some examples. So first one, well, generally here we use the nuclear technology in different fields by using the power of radiation. Okay, here also we can use the gamma rays to penetrate thick steel and concrete structures, so that we can check there are some flaws or some disperfections inside of the industrial product, and without destructing them. Also, the waste treatment, this is also important. So the radiation can change the chemical materials, can break the long chains of organic materials. In this way, the organic materials can decay faster, can be degenerated by the nature much more faster. Okay, and also this radiation can kill bacteria, can kill microorganisms, and removing contaminants. Okay, this is important. So the nuclear is not only if we didn't treat them well, the nuclear waste can be a waste, but the nuclear technology can also treat the waste. Also here, it is a very interesting example about the radioactive thickness gauge. It means that we can use radiation from isotopes to measure the attenuation of rays passing through the material so that we can determine the thickness of some industry product. Okay, it means that we don't need to contact this kind of materials or these products, but we can know the dimensions of these products. And also here are some other applications. So do you know how nuclear technologies are implemented? Okay, this one is very interesting, that we can see that even in my room here in the hotel, that it is it can give you signals when the fire happens. Means that inside of that there is an alpha emitter that it will emit alpha particles anytime. But normally, when they detect the alpha particles, so everything is fine. But when you have a fire, the fire will have smoke. Smoke will stop alpha particles, so it will give you alarm. So what is the relationship between technology, the nuclear technology and the semiconductors? Because, for example, for the semiconductors, it has to use, generally we will have PN nodes, okay, PN nodes. And for the PN nodes, we will have some electron donators and electron acceptors. So here the boron 11 will be a very good electron donators to provide extra electrons. But actually, generally in the nature, we have over 90% of boron 10, but very less boron 11. So we have to produce this boron 11 by our isotopic industry, okay? And therefore, we can have our phones, we can have our computers, we can have everything. And these applications, well, are not so good, but they had existed. Means that at the beginning of the last century, when people have found the radioactive materials, they think the radioactive material have very strong power. So they manufactured this radium chocolate, it is chocolate, and this radium butter, and also these makeups. But they thought that these things will be useful for the health of the people. But the times and facts prove that it is totally wrong. But even wrong, now you can find in different platforms, there are some magic stones or some magic necklace or something. You may find that. And they said that, okay, this magic necklace will cure every illness or give you unexpected power, okay? So if you check carefully and if you have a detector, maybe you can buy one and check if it is radioactive. So this one is also, for example, a very large space station that we can use nuclear power. And this is the source, the Shanghai source, that it can provide different kinds of radiations for different, for example, industry or agriculture and so on and so on. So actually, there are a lot of applications. At last, we will talk about the public safety and global challenges. Actually, for example, we can use these things at the airport or the railway station to check if you have a bomb or if you have knife inside it. And therefore, we can control the public safety. It is quite common. I think everyone has seen or everyone has gone through these machines. And also, we have different robots, different drones for nuclear irradiation detections, and also for the treatment of the contaminated nuclear plants, for example, for the Fukushima, for the Chernobyl. And they have already used these kind of robots and to treat this situation. And because the situation is drastic, dangerous, that it is not suitable for human beings. So we can use these different kind of robots and drones. And yes, this is a very clearly that we still have this Fukushima issue, we have Chernobyl issue, and in the future, we try to avoid any more issues, okay? For example, in the war of Ukrainian and Russian, we worried about the nuclear power plants in the war zone, okay? But if the nuclear power plants was hit by the missiles or something, the nuclear leakage is possible. So everyone has to take this as a very serious problem. And also, for example, we have to deal with the nuclear waste. This is also for sure. Yes, we have to have more standard. We have to innovate more reactors to have more technologies. And also we have to communicate between different countries, okay? We have to collaborate. And this is very, very important in the current world because the world is crazy. Okay, so we go to the summary. Nuclear science is not something distant or out of reach. It is deeply integrated to modern society and to our normal life. It will play a crucial role in the transition to a decarbonized energy's future, contributing in various ways, including hydrogen production. Beyond energy, nuclear science benefits many aspects of daily life, from healthcare and industry to food safety and even art. So I think that the nuclear power is somehow two sides of a blade. Okay, one is it is dangerous. We cannot see them, we fear them. But on the other way, if we know that, we will know how it works. We will know the principle. We will know how it can be contaminated. Okay, so we can use that, and we can use that for us. I think this is something that we need to see the nuclear from two different ways. And it is never too late to learn about nuclear science. If not before, now it is the time. Okay, thank you very much for your listening. Thank you.
Thank you, Professor Wang. And thank you for another informative, comprehensive, and really terrific presentation. Thank you very much. Now, I would like to summarize a little bit, and I like the last sentence you said. It's never late to learn about nuclear science, because I also work in the nuclear science application area, and you talked about something very familiar to me, like the HTR reactor in Shidaowan, which is produced or supported by, designed by INET, Tsinghua University, where I work here. And you also even mentioned the magic stone thing. And Professor Wang used many cases and examples to make the whole presentation very interesting. Thank you very much again. Next, I think we will have some questions from our audiences. If you have any questions, you can raise your hand and just ask them, or you can input your questions in the chat box area. Let's wait a minute for our audiences to respond. And there is an audience, Sarah, you mentioned if we can share our presentation. Actually, since this webinar was held by ANENT is an international network or regional network. It mainly operates things among the Asian Pacific area. And finally, I think we will put our videos and materials, we will upload them to our learning platform. So if your institute or your country is a member, you can apply to obtain, to get our materials. So you're welcome to join ANENT. I will show a slide, or I will share a slide that how you can join ANENT. Let's wait for our audiences to raise hands or raise their questions. When we are waiting, can we talk about something about the magic stone? Because there's a piece of news today in China about magic stone, right? It says the radiation dose is 100 times higher than a X-ray test check, right?
Yes.
So that is like also a rumor, how it can cure your body, how can it keep you healthy. So Professor Wang, do you know where is the radiation from the stone, from the rock, natural? Like when we decorate our houses, we also use these stones. Is that similar?
I think they belong to the same category because, for example, marble is the stone that we use to decorate our home, and in the marble it is mainly radon. This gas.
Yeah, radon.
It means that yes, marble will release radon in your room, and therefore, if you don't, for example, open your window oftenly after your decoration, your room will be full of radon.
Yeah. Pollution, yeah.
Yes, it is very bad for your health.
It seems that we do not have many questions yet. Let's wait for 3 minutes. Let me see who is with us. Maru and Helena. We also have audiences from Yasser from Iran and from Japan.那咱们先等一会儿，看看有没有问题。Let's wait for 1 more minute, maybe. Excuse me, Maru. If no question is coming up, I think later, maybe 2 minutes later, we can end today's webinar. Okay?
Yes, I think so. I'm also on the same page.
Okay.
Okay, let's see another question in a couple of minutes.
For your information, today's webinar is being recorded by IAEA, and we will talk about how to share them later.
Professor Xiaojun,
Yes.
we've gotten one question from Mr. or Ms. Safi in the chat box.
In the chat box. Okay. What are the most promising nuclear medicine techniques for cancer treatment and diagnosis? If it's possible to answer. Okay. If this does this question go to Professor Zhang or Professor Wang?
I think this goes to Professor Zhang.
It's a very good question and very challenging because, well, most promising nuclear medicine techniques is really a big topic, and different cancers have different kind of phenomena, and the cancer tumor cells are rather different, so we might have to use different techniques and different technologies to specifically on this kind of disease. For instance, if there are cancer tumors are in your brain or in your neck, it's probably much more efficient to use bone nutrient capture therapy. But if it's in your breasts or other locations, it's probably much better to use different techniques. So it's really cancer dependent and also depends on the patient's condition. So if we go to it very deeply, it would be a very complicated problem. But the simple answer, there is not anything most promising for cancer treatment. However, it's a rather case specifically solution. If this answers your questions.
Thank you. Okay, so maybe no more questions, and we can finish today's webinar. Thank you, Professor Wang and Professor Zhang. You're also welcome to visit INET, okay, in Beijing.
Yes, yes.
And we can, yeah. Hi, Helena, Maru. Thank you very much.
Thank you very much,
helping.
professors.
Thank you very much for coordination.
Yeah. Oh, Helena, your microphone is muted. Yes.
Yeah,
we can hear you
I
now.
would like to thank all the presenters for the really well prepared, very thoughtful, very informative presentations. So, and many thanks for ANANT for cooperation and to organizing such very nice events. Thank you.
Thank you for your support. And our next webinar will be in June. And please pay attention to our social media information and welcome to join us again. Thank you.
Thank
Okay.
you.
Thank you. Bye.
Bye-bye
Thank
then.
you.
Bye.
Bye-bye.
Bye-bye.
Bye.
Have a nice day.
Bye-bye.
I say.